Okay, so we've got this problem here from chapter 10. We actually have multiple ways of dealing with this question. Uh, like we could definitely answer this question um, using energy considerations, and actually maybe that's a useful way of starting out. That way, when we double check it with angular momentum, we will know like what's a reasonable answer. Does that make sense? Or actually,
So we just like conservation of energy?
yeah. So we're gonna start. Actually, this is strictly a. They're asking us to solve it with energy. Okay, so we'll use energy to solve this problem. So we've got two situations. We have bottom of the hill, and yep, this is exactly what motorcycles look like. And we have at least some way up the hill, and I'm not going to draw that motorcycle again. That's exhausted my artistic abilities, so I'm just going to draw a box. So here we have situation A and situation B. What kind of energy do we have at situation A?
We have kinetic energy.
We do. Anything else?
No.
That's a tricky question here. We do have one more thing. Because not only is the motorcycle going forward as a whole, but the wheels of the motorcycle are spinning. Yeah. So two kinds of energy at situation A. What about at situation B? So on chapter 7, we hadn't learned about things rotating yet. So, we simplified the, the situation. When you've got something as big as a car, you certainly do have rotational energy in the wheels, but it is small compared to the forward kinetic energy of the car as a whole. Right? But when you have something smaller like a motorcycle, the rotational energy in the wheels is actually a significant fraction um, of your total energy. Does that make sense? Maybe. All right. I was asking Casey. Before we get into our conservation of energy statement, let's calculate what the moment of inertia of these wheels are. So here we have to actually look back at problem 1015. So we're saying, it says assume that a wheel is approximately an annular ring with an inner radius and an outer radius. So we're going to make that approximation. So our wheel is basically this with all of the stuff of the wheel in here. And the moment of inertia for an annular disk is 1/2 total mass sum of the inner radius and the outer radius. Okay. We are told in problem 1015 that the mass of the wheel is 12 kilograms. And that the inner radius of the wheel is 0.28 meters, so 28 centimeters. So 0.28 squared plus, and then the outer is 0.33 squared. Where am I getting these numbers from? So problem 1033 says to refer to problem 1015. So I'm pulling these numbers from problem 1015. And this expression for the moment of inertia of an annular disk, I mean, I had it in the back of my mind, but you could always look it up on Wikipedia. And I get a number of like 1.12 for the moment of inertia here. What does it say next to the I? This is an annular disk. Annular is a fancy word for has a hole in the middle of it. Well, mathematicians and physicists love their fancy words. So, stick around, you'll hear more of them, for sure. Alright, so now that we've got that, we can... Oh, yeah, sorry, Casey. Has a hole in the middle of it. So, an annular disk is like a solid disk, except the middle's cut out, which is basically what a wheel is. So now we can do some conservation of energy stuff, right? No external forces between A and B. So the energy at A should equal the energy at B. So we have 1/2 mVA squared plus 1/2 I omega A squared equals mGHB. So we're given that our initial velocity at A, that our velocity at A is 30 meters a second. If that is so, then what is the angular speed of this wheel? Right? we've seen before that the angular speed of something spinning, yeah, exactly, Jasmine, it's v over r. And our big radius is 0.33, so it's going to be 30 over 0.33. It's going to be about 90. Right? And at this point, we have everything we need to solve for the height at B. Did a cat walk on your keyboard? My mic is off? Oh, okay. Someone want to plug this into a calculator for me? My my calculator was taken by my teenage son this morning because he couldn't find his own calculator. So he just took it to school with him. 50.6? Sounds about right. Wait. 94,536? That sounds a bit much.
Sorry, I'm a bit behind, but for the angular velocity, why did we use 0.33 for the r instead of 0.28?
So 0.28 is the radius of this little internal one. But that's not the radius that's actually touching the road.
Okay, thank you.
Yeah. $47.27. Okay. Yusuf's answer of 50 is probably not rounding G. This is about 47 meters. Okay. So then the question is, how much energy is lost to friction if the motorcycle can only coast up 35? Well then, so for part B, right, the difference in energy between A and B is going to be mg times 47, which is how far it should have coasted up, minus mg 35, which is how much it actually did coast up. And whatever the difference between those two is, that's going to be the amount of energy we lost. Where did V go in the rotational equation? Oh, I is 1.12, and then the omega we calculated was 90 rads per second. So 90 squared is 8100. Is 90 squared 8100? Yes, it is. Okay. Why did I use this formula for change in energy? I could have definitely written down, 1/2 mva squared plus 1/2 I omega squared. But all of our work in red was to show that actually the sum of these two things is just equal to mghb. So since I was running out of space, I chose a more compact form to write to write it down in. Right? Like this number here, this is the same as 1/2 I omega squared plus 1/2 mv squared. Does that answer your question, Jasmine? Or does that answer your question, Jasmine?
What about mg times 35? Is that one like is that technically? Oh, that's mghb. Never mind. Right.
Yeah. So
Okay.
the one that I've circled is mgh what we should have gotten minus mgh that we actually got.
Okay. Thank you.
Yep. The 900 is 30 squared, and the 8100 is 90 squared. Did you just magic equation me, Yusuf? All right. Do we have any comments or questions about this that are not snark, or are we good?
Dr. Wolves, I have a question. So for to find the momentum of certain shapes, do you want us to use Wikipedia or do you want to use what the book has given us?
They'd better agree. But Wikipedia has a more exhaustive list.
Actually, it looks like the book has a more exhaustive list. Like, because for some of them, I don't know, it just seems like the book has a more exhaustive list than Wikipedia.
You can use either then.
Okay.
Yeah, they will give you the same answer.
All right. Thank you.
Yep. Okay. Good problem. Who suggested this problem? This is a good one. So, serious question though. When you are doing your when you're doing your problems, you want to start from one of our main tools. So, like over here in red, we started from conservation of energy, right? And then we wrote down the energies on both sides. Right? Whereas I guess if I was being a stickler on this blue-gray thing over here, I would have said that, the non-conservative work is equal to the change in energy, which is equal to blah, blah, blah. I'm not going to ask parallel axis theorem problems. We can absolutely go over our toolbox. That is an excellent suggestion. So here's what our toolbox thus far looks like. We have kinematics. Recording's good. So we have three things that we learned in kinematics. Noting that this third one is actually not a vector equation. It's a scalar equation, so you can only apply it in one direction at a time. After kinematics, we moved on to forces. And the number one thing that we learned was Newton's second law. We also learned about some specific kinds of forces. So we learned about normal force, tension, friction, and centripetal. Where the frictional force is equal to coefficient of friction times the normal force, or the quantity of frictional force. And this is always parallel to surface. And the centripetal force, the amount of centripetal force we need to continue on a circular path, is mv squared over r. And that should always point toward the center. Okay, so I know you asked about 7 through 10, but so this is up through chapter 6, everything we learned. And just because, we learned that for the last exam doesn't mean we won't need to use some forces or kinematics from time to time on later problems. We've learned about energy, and here in green, this is the beginning of our new stuff for exam 2. Work is provided by a force applied over a distance, where the force has to be parallel to the displacement, and this causes a change in energy. The kinds of energy we know 4 different types of energy. We know kinetic. We know rotational. We know spring potential energy. We know gravitational potential energy. No, I use capital T for kinetic energy. And actually, capital T is the usual variable that people use. just because K gets used for so many other things. And yeah, I know T gets used for time, but K appears like literally everywhere. Yeah, it's true. The lab book uses a different notation as well. And then we've learned about momentum. And we know about linear momentum, where the momentum is equal to the mass times the velocity. And an impulse is provided by a force acting over a time. And that causes a change in momentum. We have also, in this last chapter, in chapter 10, learned about angular momentum. Impulse is J, P is momentum. Yep, those are historical letters that we are stuck with. So in this last chapter, we've learned about angular momentum, which is I times omega. And we have a similar impulse momentum theorem where a torque applied for a time causes a change in angular momentum. And then lastly, because it doesn't fit in too super neatly in other places, I'm going to talk about torque. Q goes the other way, William. Torque. A torque is caused by a force acting perpendicularly to a lever arm. And the rotational version of Newton's second law is that sum of torques equals I alpha. Okay. You might also make a note about rotational coordinates, I suppose. So since we've got some space, let's summarize that here too. Right, so we have analogs of position, velocity, and acceleration in rotational coordinates. Our kinematics work in rotational coordinates, so we can have for example. And yeah, I think that's everything. This is everything we've learned this semester. Questions or comments?
Dr. Wolfs, if we do use a magic equation, what do we have to do to not lose points?
So if what you're using is not on this list, because what the things that are on this list are generally true. If you want to use something from the book that's been solved in a different form or something like that, you have to note what the limitations of that formula are and show that this situation you're applying it to satisfy those limitations.
So if we just include the exceptions to the rules, like will we get full points for it?
What do you mean by exceptions to the rules?
Like let's say okay, oh this don't this like let's like for example, like changing momentum, right? And we set to like let's say we just set two equations equal to each other and say that L equals L. Well we can if we write like oh this only applies when external torque forces are zero. If we do that, will that be okay?
Yeah, that's fine.
Okay, and also so anything that's not in this list is considered to be a magic equation, right?
Yes.
Okay,
Anything that's
thank
not
you.
in this list is only true in specific circumstances rather than generally true. And so if you want to
Okay.
use a specific equation, you need to, yeah, every specific equation has limitations and you need to be aware of it and show me that you're aware of it.
Yeah. Okay, thank you.
Yeah, you're welcome. Simple machines. Maybe. The simple machines section though is literally just torques, right? Like levers, right? If you're in a lever problem, you're just going to be looking at torques. So there's nothing new in the simple machines section, basically. Got to make half the exam about simple machines. I feel like that's a bit much. Yeah, I'm definitely not going to do that. But
began as cumbersome.
what I would recommend to you is this video that I'm about to link by the engineer guy. Now that you know about rotations and moments of inertia, you are ready to understand, to analyze how a music box works. And I think that's delightful. So he does a great uh, explanation of how music box works, and you should definitely take a look. So, Casey, we can definitely do more problems from 9 and 10. Um, yeah, here we go. Yusuf, chapter 9, number 18. Oh, I mean, we great minds think alike. 918 it is. Yeah, this question is great. Let's see, which one of these pictures do we want? Start with one in figure 1920. Okay. All right. So the center of gravity of the pole held by the pole vaulter is 2 meters from the left hand, and the hands are 0.7 meters apart. Calculate the forces exerted by his right hand and his left hand. If each hand supports half the weight, okay, and then, yeah, we'll go on to a slightly different. Okay. Yeah, great problem, Yusuf. Thank you for asking this problem. This diagram is actually pretty good. So it's labeled the 3 forces that are at play on this this pole vaulter, and it's given us a free body diagram here. There are some distances involved, so like from this hand to the center of gravity is 2 meters, and the distance between the two hands is 0.7 meters. Okay. Is the pole vaulter holding the pole steady, or is it dropping? Yeah, it's steady. If it's steady, right, and we're gonna for the force part of this problem, we're gonna say that up is the positive y direction. If he's holding it steady, then sum of forces equals 0. So if the pole vaulter was in the process of like dropping the pole, then the pole might be accelerating toward the ground, in which case the sum of forces wouldn't be 0, it would be some acceleration, times the mass. Does that make sense? So if an object is not moving and it's steadily not moving, like not accelerating, right? Then that must mean that the sum of forces is 0. Because if the sum of forces were not 0, then it would only be temporarily stationary, and we would be accelerating somewhere, and the pole would immediately start moving. Right? So if we are in a steady equilibrium, right, position is the same, velocity is the same, then there's no net force. Does that answer your question better, Casey? Yeah, if it's moving and accelerating, then the sum of forces is not 0; it's ma. But in this case, I mean, when we write down sum of forces equals ma, the acceleration is 0, so whole right hand side is 0. You could. The Why is it FR instead of minus FR? Oh. Yeah, Jasmine, you're totally right. We could have problems where the sum of forces is not 0, but 0 is just such a convenient number and lets us do, do calculations more conveniently. So, I mean, it's less likely. But we could definitely see a problem where there is motion and is rotation.
I have a quick question. So if we push the pole down, isn't it gonna go like counterclockwise? So like, why do we switch it to negative?
So we're not thinking about rotation yet. We're just thinking about up and down movement. So we will definitely get to rotation in a moment.
Oh, okay.
But good question. Okay. Okay. I think, unless there's no other questions, I think this is the end of what we can do with forces here. Right? Because we have two unknowns, and so the force on the left and the force of the right hand are unknowns. We're going to say that the weight of the pole is known, even though they don't give us a number for it. But so we want to write down FL and FR in terms of W, and we can't do it with the green work alone because that's only one equation and we have two unknowns. So that's not going to give us enough information. Now we deal with torques. You're exactly right, Jasmine. For torques, we are going to say, right, that torques that would cause a rotation in the counterclockwise direction are positive. And we have to make a choice. Where is the axis of rotation for this pole, right? If the thing is not rotating, then it's not rotating about whatever axis of rotation we choose. You want this axis of rotation at the center of gravity? I think that's a good choice. So Yusuf, it won't change your answer to put the axis of rotation at different spots. What it will do is make the algebra more convenient. So with the axis defined at the center of gravity, which is a great choice, if the pole is steady, it's not moving, that means it's also not rotating. If it's not rotating, then the sum of torques has got to be 0. And the torques that we have here, is weight also always at the center of gravity? Yes. So the weight is at a distance of 0 from the axis of rotation, so it doesn't actually produce any torque. And then we have FL, which is going to tend to make this whole thing rotate clockwise. So that's a negative torque. And it's 2 meters from the axis of rotation. And then we have FR, which is going to tend to make the whole thing rotate counterclockwise. So it's positive. And it's 2.7 meters from the axis of rotation. All right. So far, so good? Questions, comments? Nope, good. All right, let's solve. Is that omega or work? Are you throwing shade at my handwriting? Again? Yeah, this W is the W that we're given in the diagram here. So since it's applied at a distance of 0 from the axis of rotation, that does 0 torque. So we end up saying that 2.7 FR minus 2 FL is equal to 0. And now, looking back for a moment at the Green equation, I think it's convenient to say, well, FL is equal to W plus FR. So we can say 2.7 FR minus 2 times W plus FR equals 0. So that's going to give us 0.7 FR equals 2W. And then what's 2 over 0.7? Someone with a calculator? Someone whose son did not steal their calculator this morning? $2.857. Sounds good. Okay. So the right hand has to exert almost a force equal to almost 3 times the weight of the pole. And that must mean that FL is equal to weight plus FR, which is 2.857 weight. So the left hand has to exert a force that's almost 3 times bigger, or 4 times bigger than the weight of the pole. In other words, this is a pretty inefficient way to hold a pole. Questions or comments on this bit?
Where did you get the 3.857 from?
The 3.857? It's because 1W plus 2.857W is 3.857W.
But like, where did that one come from? Like, we don't know what W is.
We don't. We don't know what
so
W
say
is.
that.
Yeah.
Oh.
So it's just in term. It's in terms of a multiple of the weight of the pole.
Okay.
So how do I know it's inefficient to hold this bar like this? Because the total force we're exerting, right hand and left hand, is more than 5 times the weight of the pole. Whereas if we had just held it in the middle, we could have exerted a force equal to just barely equal to its weight. Would we say FR is negative since it's pointing down? Yes, but we handled that negative sign up here. Well, in this problem, we can't go any further because we don't know what the weight of the pole is. I suppose you could look it up. I mean, you've got access to the internet, so you'd be like, Google, how heavy is a pole vaulting pole? Actually, you know what? That's not something I know, so I kind of want to look that up. Holy crap. These things are like 40 pounds. The pole is 40 pounds. So as you're running up to do your vault, you're like, the force of holding the pole is like holding a 200-pound object. That seems wild. Is the direction of the force and its equivalent torque usually opposite? No, not necessarily. So you need to be careful about what the positive direction is for each different kind of analysis. So if we had decided that our axis was at the right hand rather than at the center of gravity, then the directions of our torques would be different. That's true. Up is usually positive, counterclockwise is usually positive, but where you put the axis of rotation determines which force is actually moving in a clockwise or counterclockwise direction. So when we put the axis at the center of gravity, FR was moving in a counterclockwise direction, whereas FL was moving in a clockwise direction. But if we put the axis on FR, like on this right hand, then FL would be moving in the counterclockwise direction, and W would be moving in the clockwise direction. Yes, it is weird to think about. And in fact, it's going to get worse in part C of this problem. Clockwise is our negative here. And yeah, Jasmine's exactly correct. No matter where you put the axis, you're going to get the same number, but your algebra will look different. Okay, so for part C, we have a slightly different diagram. And part C explicitly says, show that you don't have to use center of gravity as the axis of rotation. We did do part B, so parts A and B were left and right hand. Okay, so in this situation, we are holding the pole like a normal person. And yeah, Jasmine, that's exactly right. We're going to choose, in fact, we're going to choose a point, spoilers, we're going to choose our axis of rotation over here. So the axis of rotation is going to be 2 meters to the left of FR. FR is going to be 0.35 meters from the center of gravity, which is then 0.35 meters from the left hand. So the force analysis was already done for us, right? They said, FR equals FL equals 1/2 of the weight, right? Which is how a normal person holds things. They distribute half the weight to each hand. So now, we can do torque analysis. And again, we're going to say that clockwise is the positive direction. And since this pole is being held steady, we know that the sum of torques is 0. And the torques that we've got here are Fr times the distance to the axis, which is 2. Is Fr going to be a clockwise or counterclockwise torque? Right, we have both possible answers in the chat. So Fr is going to be going starting up and over. That's the clockwise direction. So that'll be a positive. Similarly, FL will also be a positive torque. Just so I kind of imagined what direction Fr is going to point as this thing rotates, and it's going to be pointing, right, its change in pointing is going to go in the counterclockwise direction. So it's a positive torque. Did I say counterclockwise? Did I say clockwise? I meant counterclockwise. I think we should bring back the term Widdershins for rotation. It's an Scottish word, I think. Widdershins is Scottish for counterclockwise. And then docile is clockwise. Those words have fallen out of use, but I think they are lovely kind of words. How does the force make the object move counterclockwise? Okay, so what we have to do is we have to imagine that the only force we had was Fr. Right? If only Fr, if Fr was the only force on the pole, and we had bolted the pole in place at the axis of rotation, right? Then Fr would tend to cause that pole to rotate counterclockwise, right? It would move the long end up, and then to the left, and then down. Does that make sense, Yusuf? Oh, I was saying, if we bolted the pole to the wall at the axis of rotation, and the only force was Fr, then Fr would tend to cause that pole to rotate counterclockwise. Right? It would move the long part up, and then to the left, and then back down. Right? Exactly. FL is going to tend to cause exactly the same kind of movement. Yes, and if the axis was on the other side, Fr would tend to push that long side down and rotate it clockwise. Or sorry, not down. It would still move it up, but it would move. Okay. Let me back up. Take a breath. Yes, if we had the axis of rotation over here instead, then Fr would tend to rotate this thing clockwise, right? Because that's where we the X is where we had bolted it to the wall. So where we imagine the axis of rotation to be makes a huge difference in which forces produce positive or negative torques. So if the axis is where we've chosen it in green, then the only negative torque is actually caused by the weight. Did I answer everyone's question? If I missed you, please speak up. Cool. Now that we've written out the sum of torques, we actually can use this information that the problem gave us about forces. So we have 2, weight over 2, plus 2.7 weight over 2, minus 2.35 weight. So these 2's are going to cancel. The 2.7 divided by 2 is going to be 1.35. And so if we add these together, we've got 1W and 1.35W for a total of 2.35W. So what we've just shown is that if an object is not rotating, you're free to choose the axis of rotation wherever you like, because it's not rotating around all of those points, right? This pole is not rotating at all, which means it's not rotating about the center of gravity. It's not rotating around FR. It's not rotating about this green point, and it's not rotating about this orange X either. So we're free to choose any of those points as the axis of rotation, whatever seems convenient for us.
Dr. Wolves, you wrote 2.35W instead of 1.35W.
Well, we have 1.35 from this term plus another 1 from this term.
Oh, I'm sorry.
Yeah. It's a good question, though. What would the weight be? Still no idea. Why did I write W over 2 for FR and FL? That information was actually given in the problem statement. So Casey, because it's 0, torque rotation is not occurring no matter where we place the axis. Exactly. If an object is rotating, then it's rotating around one specific axis. But if it's not rotating, then it is not rotating about every point that you could choose. Hell, we could choose an axis that's not even on the pole. We could actually choose our axis of rotation up here. It's also not rotating around that blue spot. Can we do 10.17 next? You bet. Hey, you picked a novel. An automobile engine produces a certain amount of torque. If 95% of this torque is applied to the drive shaft, axle, and rear wheels of a car, it's reasonable. Most of the torque your engine makes actually goes into spinning your wheels. Assume that your car is in the shop and they've got it up on one of those big lifts that lifts the wheels off the ground so that mechanics can work on it. So if that's the case, then the wheels can turn freely. Each wheel is basically a disc. The walls of the tire are like an annular ring. And the tread of each tire acts like a hoop. So this is a little bit more precise than the problem we did with the motorcycle, right? Where they're just like, yeah, the motorcycle wheel is basically a ring, whatever. Or here, we're saying that to be more precise, like our car wheel has several parts. So it's got an interior wheel that is more or less solid metal. And then around that, there's the body of the tire. And then around that, wait, hold on. There's a circle drawing tool here. Why am I trying to freehand a circle? All right, so we have a solid inner bit that is basically solid metal. That's the wheel. And then outside of the wheel, we have the walls of the tire. And then outside the walls of the tire, we have a relatively thin layer of tread. And each of these has different densities and different distribution of masses. So we'd like to deal with each part of the tire individually. And then we also have the axle, where the axle, we're just going to treat it like just a cylinder, basically. And then we also have a drive shaft. Okay, so we label these. This is the axle. This is the drive shaft. And this is, maybe we call this the compound wheel. Yep, recording's good. I actually figured out what was causing it to break. And it's when I share a Chrome screen or stop sharing anything else, the recording breaks. But I don't know why that is necessarily, but that is apparently what happens. Okay. So we want to know what's the angular acceleration of the whole drive assembly of the car. And we know that torque equals I alpha. So the angular acceleration of the whole assembly is going to be equal to the torque supplied, which is 200, over the total moment of inertia. the kind of beautiful thing is that moments of inertia are just additive. So if you have multiple components in a rotating system, the total moments of inertia is equal to the sum of all the individual moments of inertia. So the moment of inertia of our whole arrangement is going to be equal to the moment of inertia of the drive shaft, plus the moment of inertia of the axle, plus the moment of inertia of the inner wheel, plus the moment of inertia of the tire wall, plus the moment of inertia of the tread. So far, so good? All right. So the drive shaft, they tell us, acts basically like a rod. So if we're rotating about our center axis, the moment of inertia of a rod like that is equal to 1/2 mr squared. Actually, let me organize this a little better. All right, so this thing, I is mr squared, 1/2 mr squared. The axle is also going to be 1/2 mr squared. The compound wheel, it's going to be a little bit more. But yeah, a disc or cylinder or rod, right, all on their main axes is 1/2 mr squared. Remember, for an annular disc, we saw this one at the beginning of our office hours today, is 1/2 m r1 squared plus r2 squared. And then lastly, a hoop is just mr squared with no half. Okay. So our drive shaft is going to have a moment of inertia of 1/2. Mass is 30. Radius is 3.2 centimeters. So 0.032 squared. The axle is going to have a moment of inertia of 1/2 m, which is 14, and then r squared. So r is 2 centimeters, so 0.02 squared. The wheel, which is they're telling us to treat as a solid disk, is going to have a moment of inertia of 1/2 m, which is 15 kilograms. And then r squared, so that's 0.18. And there's also the tire wall, which is an annular ring. So 1/2 m, which is 2 kilograms. 0.18 squared plus 0.32 squared. And then lastly, the tread, which is just mr squared. So 10 times 0.33 squared. And then last consideration, there are actually 2 wheels. So this whole thing needs to be multiplied by 2. Yeah, so an annular disc is basically a solid, but has the center of it cut out, whereas a hoop, all of the mass is at the outer rim. There's no mass at all in the inner rim, in the inner parts. Okay. Questions or comments? No questions? Okay. .8, number 52. Is that what you're asking there?
Yeah.
Okay. Let's take a look. Number 52. My copy of the book only has 48 problems in chapter 7.
Okay.
So
That's weird. Yeah.
where can you can you tell us what the question is about, maybe?
Yeah. The question is, let's see here. So a person's jumping from some height to the ground. So part A is calculate the magnitude of the force produced if an 80-kilogram person jumps from a 0.6 meter high ledge and lands stiffly, compressing joint material 1.5 centimeters.
Okay.
And then part
Oh.
B is
Sorry, I found the question you're asking for.
okay.
I don't know why it wasn't showing up the first time. Here it is. Is this the question you were asking for?
Yes.
Okay, cool. All right, cool. So we have two situations. Situation 1, we are on top of a ledge here. Situation 2, we're down here. And we're on the ground. So we want to use energy to try and analyze this. We'll call this situation A, situation B. At situation A, we've got gravitational potential energy. What kind of energy do we have at B? Well, we don't have kinetic because we are standing on the ground. Yeah, we have nothing. Yeah, we're gonna get to that in just a moment. So there are actually two perspectives that we could use to solve this problem, and I'll go over both of them. So the first perspective, we are going to consider that our bones provide forces that do work, rather than being sources of potential energy. So if we view our bones as providing forces that do work, then we have, work is a force applied over a distance, and that causes a change in energy. All right, so here, we will, of course, say that up is the positive direction. So here, the force that our bones are exerting is in the positive direction. It's up, like we wants to stop our velocity. But the direction in which our bones are compressing is negative. And then what we mean by change in energy is just the energy at situation B minus the energy at situation A, which is going to end up being 0 minus mgh, so minus mgh. There we go. So the average force that our bones must exert is equal to mgh over 0.015. Which is equal to 80 kilogram person. So 80 times 10 times 0.6 all over 0.015. So in this problem, we are considering gravity as a source of energy rather than a force which does work. So yeah, if we want to pull a force out of an energy analysis, it means that the thing providing the force can't be a source of energy. But here, we're not trying to pull weight out of our analysis. We're trying to pull the bone force out of our analysis. So bones have to be something that provide forces that do work, and bones are not sources of energy. But we already have the weight, so we can go ahead and deal with it as a source of energy or a force. Like, either way is going to be fine.
So then for part B, would we just replace the 0.015 with a 0.3?
Exactly. So if we're stopping over a distance which is 20 times larger, then the force is going to be 20 times smaller.
Okay, thank you.
So Jasmine, I'm glad you asked that question because that is actually what I was going to talk about next here. What if we viewed the bones as a source of potential energy instead? Well, we could say that instead of saying there's no energy at B, we say that there is some spring potential energy at B. Where these, quote unquote springs are actually our bones, right? So anything that gets compressed elastically is basically a spring, as far as physicists are concerned. So we could totally say, in that perspective, work equals forces applied over a distance, but in this case, we're not looking at any forces, we're only looking at sources of energy. So here, there's no change in energy, which means energy at A equals energy at B. So we have mgh equals 1/2 k delta x squared. So the information that we get out of this analysis, even though it's exactly the same situation, the information that we get is not the force exerted by our bones, but the spring constant of our bones. The spring constant is a force per meter of compression. So this ends up being actually a pretty large value, so our bones are relatively stiff. Which is good, considering all the walking and jumping and stuff that we do to them. Questions or comments?
Dr. Wolfs, why is the change in energy like 0 again?
It's a different. So in purple and red are two different perspectives on the same same situation, right? So in red, we said to ourselves, all right, bones are things that provide forces, and those forces do work. And we did the analysis, accordingly. In purple, we said, well, actually, bones aren't things that provide forces. They are springs that are sources of potential energy. And we did the analysis accordingly. Both red and purple are true. But because we're talking about them in two different perspectives, we get two different kinds of information out of our analysis.
So, we can't say that it provides spring energy, potential energy, and it can't be a force and it can't bring force and spring potential energy. Is that what you're saying? Like we can't say that it provides both?
Yeah, we can't say that it's both at the same time.
Why not?
Because they'll just cancel out.
Okay.
Right, and we'll end up getting a statement that says 0 equals 0, which is true, but not helpful.
Got it.
Any other questions, comments? I think we have time for one more problem. $9.14. You know what I need to do? I need to figure out a way to put the chat scroll on top of the video so that when you watch it on YouTube, you can see what people asked in the chat. Yeah, like a real streamer. Mm-hmm. Thanks, Yusuf. All right, here's the problem that Yusuf was asking for. So there is a chain in between the two halves of a sandwich board. There is a hinge where they are allowed to rotate. Okay. Let's go. We need to add a little more detail. So what I would like to do here is just analyze the right half of the sandwich board. And since the whole thing is symmetrical, we're going to say that exactly the same thing is happening on the left half. So the chain is exerting a force like so. It's going to be at an angle here. And that angle is going to be the same as the angle between the ground and the sandwich board leg, since the tension is parallel to the ground. Right, so before we do anything else, let's figure out what that angle is. Right, so if we draw just half the sandwich board, and we want that angle there. From the diagram, like the length of this side is 0.55 meters and the height is 1.3 meters. So the angle is equal to inverse tangent of 0.55 over 1.3. That's like 23 degrees. Okay. So far, so good?
Dr. Wolves, could we
Yeah.
have like also done like where we just do like we multiply the 0.50 and just like t like this and then just do that to find our Or what are we trying to find here? Are we trying to find like torques or something?
We are going to do torques, and since we kind of know that we're going to have to do torques, like I know that we're going to need the angle between the tension and the sandwich board.
Well, can we do it without like figuring out the angle? Because I think we could just find the torque. We could just multiply 0.50 and 0.55 without doing the
Um,
sine thing.
So 0.5 and 0.55.
Because that's the force of the tension, right? That's what I'm assuming.
So what is
Or
0.5?
the chain. Or I don't know where you got 0.55 from.
That's half
Oh,
of this
the
length.
okay. Okay. Oh, so we're just measuring we're just doing distances right now,
Yeah,
not
so
forces. Okay.
that's
Oh,
right.
I'm sorry. I'm sorry.
Okay. There's like, wait a minute. Yeah, we're not. Yeah, these are just distances so far. So 1.35 meters, or sorry, 1.3 meters tall, 0.55 meters wide. So that gives us the two legs of this right triangle that we would get if we draw an altitude directly down the middle of the sandwich board. Okay. So far, so good? Yeah. What I would actually like to do is is draw this out with the sandwich board kind of laying flat to make it easier to see things. So if this is one half of the board, there's the center of gravity. Um, there's where the tension is at. There's where the hinge is at. Also, I just realized did this thing backwards. This should be 1.3 over 0.55. Opposite over adjacent. So that's not 23 degrees. That is 90 minus 23. So 67 degrees. Okay. So the weight is coming off the sandwich board the board at an angle, and that angle is going to be 23 degrees. This is our mg. The tension is coming off like so, and that angle is 67 degrees. And then there's also a force exerted by the hinge, which is I mean, spoilers, I'm not going to care too much about the hinge since that is what I'm going to choose as the axis of rotation. The distances are also going to be, we take a little work to get at, right? So this distance here, that's going to be the, this distance right here. And we have to be, so sine of 67 is going to be equal to opposite, which will be the vertical distance, over the hypotenuse, which is actually the thing we want. So R1 is equal to a half over sine 67. So that's what this is here. 0.5 over sine 67. It's R1. Yeah, let me redraw this triangle a bit. So this is the distance we want. Our angle is 67, and we know the vertical part of this is a half. So sine of 67 is 0.5 over R1. Because if we want to calculate how much torque the tension is exerting, we need to know not just the amount of tension, but how far from the axis of rotation is it. For the weight, we're going to do a very similar thing. Right, same angle, except the height that we've gone down is half the total height. So it is 0.65. Yeah, when I said we had time for one more problem, I basically meant any problem except this one. But we're actually we're close. We're almost to the payoff. If this sandwich board is sitting stably on the sidewalk, then the sum of torques on each half of the thing must be 0. And the torques provided are, there's one torque due to the tension, and if we look at the direction that the tension is pointing, that is going to tend to be, actually hold on a second. Did I draw this thing correctly? Yeah. I mean, both of our... Okay. We've definitely missed something here, right? Because both of these forces appear to be making a clockwise torque. And I think I see what's going on, but unfortunately, I have a parent-teacher conference with my son's teacher in like 3 minutes. So I can't, I really can't stay and go over. So, oh no, this is definitely not going to be on the exam. This is like this is like 3 steps of geometry just to get started, I'm not gonna ask that big a question, for sure. That's too much.